read this. I'm going to read this paper. It's looking good.
Now we will hear elaborate on toy quantum categories.
Yeah, looks good.
Okay.
The time it's down to the last second, so hopefully we'll be able to fit it all in. Okay. Right, for several years now, I guess various groups have been looking at re-expressing quantum mechanics in terms of category theory instead of the normal vector space formulation. You've seen a bit of that in the last few talks. I guess there's various motivations for this. I'll just say a couple of words about one which might make sense to a physicist. Quantum mechanics is quite a successful theory as it stands, but I guess the consensus is that in order to bring it together with, say, general relativity, it may need to be fairly heavily modified, and how exactly that's going to happen is not really that clear. Now, with a slight change of perspective, quantum mechanics in its existing form can be seen as being expressed in a category, a particular category, Hill. Now, I guess, in essence, the first step in our research program is to sort of identify the features of this category Hill that allow it to describe the observed behaviour of quantum systems. And I guess then the second natural step is to look for categories which share some of these features and would thus provide models of at least some aspects of quantum behaviour. I guess the ultimate aim would be that we want to find a category which is different from Hill, which replicated all of the observed quantum behaviour, but which I guess was more amenable to unification with gravity or something like that. Now, we're not really anywhere near that, but let's see how far we've got. Quite a lot of progress has been made with the first part, identifying the quantum features of Hill, and that's going to be the subject, along with a short introduction to category theory. That'll be the subject of the first part of the talk. Recently, we've been looking at the sort of the second step, looking for some sort of concrete models of other categories which share these features with Hill. And I'm going to be talking about two particular categories, rel and spec, which replicate some features of quantum mechanics. Both these categories are going to be, they're kind of small or discrete in a sense, in that their Hom sets, for those who are familiar with the term, are finite. And so certain questions about these categories can be sort of settled by brute force calculation, whereas in, say, in Hill, more sort of subtle proofs would be required. So neither of these categories really is a perfect model of quantum mechanics, but they may be useful in settling certain questions about categorical quantum mechanics. In the last part of the talk, I'm going to discuss how this category spec relates to a toy theory of quantum mechanics proposed by Rolf Speckens, hence the name. Okay, so I really wasn't sure how much background in not quantum mechanics, of course everyone's got a pretty good background in that, in category theory people had, so I will quickly discuss some ideas. I don't think, if you know nothing about quantum mechanics, then some areas of this talk might be a bit opaque, but hopefully I'll be able to say enough that you can follow it in outline. A category is an algebraic structure, and there's two types of sort of elements in the category. There are objects and there are arrows. So here you've got a diagram of a part of a category. Now the objects have no algebraic structure themselves, they just give an overall structure to the category. And the algebraic structure is on these things here, the arrows. Now, essentially, the algebraic structure is that if we have an arrow like this F going from an object A to an object B, and we have an arrow H going from object B to object C, then we can combine these, and these map into an arrow going from A into C. So, for example, we might, in this case, have that the arrow K is equal to the composition of H and F. Just a few bits of notation. This is how we denote that we have an arrow F going from A to B. By this here, this is what we call the Hom set of A and B. This is the set of arrows going from A to B. What else I wanted to say? Just a quick sort of. I've presented a category here as a completely abstract sort of structure. In fact, frequently we're really interested in specific examples of categories, and the most sort of common examples we've got are where the objects in the category are mathematical structures and the arrows are structure-preserving maps between these structures. Examples, the category set, where the objects are sets, the arrows are functions. A completely different category, rel, where the objects still are sets, but now the arrows are relations. And so on. Another sort of example I could give of a category would be, I guess, this sort of putative category quant, where the process, where the objects are quantum systems and the arrows between them are quantum processes. Now, as we understand quantum mechanics at the moment, quantum systems are described by Hilbert spaces and the processes that they undergo by linear maps, and so existing quantum mechanics is essentially described by this category here. Okay, so what are the properties of this category here that make it more suitable for the description in quantum mechanics, say, than this one here? Well, several things. First of all, Hilbert is a symmetric monoidal category. We saw what the definition of that was a second ago. I don't have a blackboard. By symmetric monoidal category, I'll run through this very quickly because I've been in the other talks. We have an operation. Given two objects, A and B, we can form a new object like that. Given morphisms, F and G, maybe we can form a composite of them as well. This operation here is associative up to isomorphism and also symmetric. And furthermore, we have a special object I, such that this is the case. What I mean by isomorphic is, well, in a particular sort of category theory sense, which I don't really have time to go into. We represent, we use, I will make use of graphical language, which has already been introduced for these symmetric monoidal categories. Just to give an idea of what we sort of intend as the physical interpretation. When we've got two systems here, represented by A and C, tensioning them together, the object A tensor C represents the composite system, viewing these two systems as a single system together. I should also note that any morphism or any arrow of this type here, where we go from I into A, we sort of imagine that as representing the preparation of a system A in a particular state, say psi. Okay, we need a little more structure. Obviously, the adjoints are an important. The adjoint of a linear map is quite an important concept in the standard presentation of quantum mechanics, and we need a kind of an abstract counterpart to that. That was already introduced by, I think, the two previous speakers, so I can sort of run through this very quickly, just recap. that if we have an arrow going from A to B, then there's always a corresponding arrow going from B to A. It's actually a contravariant functor, and furthermore it's involutive. So for example, there's no such structure on the category set, but there is on Hild by taking the adjoint, or on the category rel by taking the relational converse. In a dagger symmetric monoidal category, these two structures sort of fit harmoniously together. That won't make any sense if you don't know any category theory. Okay. Now, as it stands, there's nothing. Well, we haven't really got to grips with what's this sort of quantum about Hild, and I guess one of the really key features of quantum mechanics is the existence of incompatible observables, and so we'd like some sort of abstract way of talking about them. So how does quantum mechanics, how does the category Hild do this? Well, we're going to have something we're going to call might be able to tell I've reused these slides, but I get a bit kind of sometimes it's an observable structure. In this talk, it's a basis structure. A basis structure is it is a. Christ, what is it again? It is a co-commutative co-monoid. What that means is that we have an object X and two morphisms or two arrows here, such that here they are represented in the graphical form, and these laws here need to hold. These two, which Jamie mentioned a minute ago, and this one here, co-commutativity. For those familiar with symmetric monoidal categories here, this crossing here represents the symmetry isomorphism. Now, we're going to require two further laws to hold for something to be a basis structure. The Frobenius law, which we saw a minute ago. I should note, I go left to right as well, following Peter Selinger. One of my supervisors goes top to bottom, the other goes bottom to top. It's a bit mindful. And furthermore, the isometry law. Now, we're going to say that these are the abstract counterparts of orthonormal bases. Now, what allows us, what's the justification for that? Kuka, Pavlovich and Vickery, really done, have shown that, in fact, in the case of this category FD Hill, where our objects are finite dimensional Hilbert spaces, these basis structures and orthonormal bases are in bijective correspondence. The actual sort of way that bijection works in practice, if we've got an orthonormal basis of these vectors here, AI, then the delta morphism basically copies these basis vectors, and this epsilon uniformly deletes them. Now, so we've got an idea of this gives us an abstract sort of counterpart for an observable. We'd like to be able to talk about incompatible observables. In fact, we're going to sort of specialise and talk only about mutually unbiased observables. Mutually unbiased observables would be those. We've got the slide with the definition. For example, things like position and momentum, or spin X and Y. Cases where if you're in one basis, then you've absolutely no knowledge about the other observer. Now, how do we? What's the abstract counterpart of that? To give that, I'll have to give a couple more definitions. Now, we say that a state here is classical with respect to a basis structure if this equation in the graphical calculus holds. Essentially, these are the sort of abstract counterparts of the basis vectors, and if this thing is copying them, then these are the classical states. Slightly more opaque is this definition here of an unbiased state. Here, this is the adjoint of the delta map, and if this thing here is unitary, then this state here is unbiased with respect to this basis structure. Now, given two basis structures, if all of the classical states of one basis structure are unbiased with respect to the other, and vice versa, and we have mutually unbiased observable structures. Now we're going to claim that these are the abstract counterparts of mutually unbiased bases. How do we justify that? Well, all of these categorical properties are in the category FD Hill. All of these are satisfied by mutually unbiased bases. And I suppose, perhaps more convincingly, we can use these definitions to model the correct behaviour of protocols and algorithms which rely on mutually unbiased observables. That's all in the work done by Bob and Ross. Okay, can you even see that? No. Okay. Right, so we're now going to look at a couple of actual concrete examples of these categories. And I will begin with this category here, FREL. The objects of this category are finite sets, and the arrows of the categories are relations between them. It's a dagger symmetric monoidal category. This operation here is given by the Cartesian product. The identity object is the single element set, and the dagger operation is the relation converse. Now, let's consider first of all the smallest kind of non-trivial object in the category, which is two-element set 0 and 1. And we would imagine that this would sort of describe the simplest system that this theory can model. Something maybe analogous to a qubit in the case of the category Hill. So if it's going to describe something quantum mechanical, then it's going to need to have these mutually unbiased basis structures. So do we have any basis structures in this case? Yes, we do. So, okay. Okay, so the first basis structure on this object 2 is given by these two morphisms here, the delta and the epsilon. These are relations between the two-element category and the two-element object, two-element set, and the Cartesian product. I've sort of made a sort of convenient grid notation for these relations here. It's fairly clear. This grid represents the Cartesian product of these two. This thing has, this basis structure here has two classical states here, given by the Z0 and Z1, and one unbiased state here, X0, of this form. Now, initially we thought this was the only basis structure on FRL, but in fact there is a second here, like this. This appears to be quite different. In this one we seem to sort of copy the 0 and the 1, and here we've got something rather different. If we look at the classical and unbiased states here, we can see that these two basis structures are mutually unbiased, and therefore in a sense we can sort of model certain aspects of quantum mechanics in this category. I should go back and compare this to the basis structure in FD in the category Hill, the standard quantum mechanical category. In that case, remember the slide I put up before, the deltas are given by these copying operations, for example. And there's a clear analogy between these two basis structures, but this one looks quite different. Doesn't seem to be sort of analogous to the structure in Hill. However, if we remember that that there is a basis structure of this sort for every orthonormal basis, then, for example, this one also is a valid basis structure in FD Hill. And if we rewrite that in the 0-1 basis, then we get something much more analogous to this one up here. I think it's, we can make a basis structure in Hill analogous to this one by performing a change of basis. Of course, in the category FRL, there's no notion of changing a basis. And so, in FRL, at any rate, these two relations appear to be quite different. However, you have to sort of look at their categorical properties to see the similarities, which are sort of manifest at the concrete level in the case of FD Hill. Okay, how have I got? Right. Now, there are two basis structures on this object in FRL. However, this weird sort of asymmetry in the where do I put that one? In the numbers of classical and unbiased objects makes it a rather strange sort of object. It's not really much like a qubit, and we can kind of rectify this by moving towards another category, which is actually a subcategory of this one, but gives a somewhat better model of a qubit. This is the category that we've called spec. Right, the objects of spec are the single element set, the 4-element set, and Cartesian products, arbitrary Cartesian products of these. The arrows are the closure under composition, Cartesian product, and relational converse of the following relations. All permutations on the 4-element set, there's 24 of them in total. This operation here, which I've denoted again with this sort of grid notation, it's be a lot clearer than writing it all out in this case. And this operation epsilon again, which I've written in the grid notation. Right. This category is a dagger symmetric monoidal category. It inherits all the relevant structures that FRL had. Does it have basis structures? Well, yes. It is fairly straightforward to verify that this is a basis structure. I've ruined these slides. The unbiased and classical states of these, we get the unbiased states, well, if we take epsilon z and take the dagger of that, then we have a morphism or an arrow of the form I going into 4, which is the right sort of form for a state. and we can then get these further 5 states by applying permutations to x naught. And for this particular basis structure, these 4 states are unbiased and these 2 are classical. In fact, there are this object 4 has 12 basis structures. They all fit. This slide stays up for an unreasonably short time, given how long it took to write. Now, these sort of fall into 3 clear families corresponding to these 3 rows, which all have the same unbiased states and classical states within the row. And if you comparing these classical and unbiased states, we see that you've got basically any basis structure in one row will be mutually unbiased with respect to any basis structure in another row. So, in essence, these give us 3 mutually unbiased observables, each with 2 classical states, and so we have something somewhat more like a qubit. Okay. I'm just going to very quickly at the end add a little bit on how this category spec with this, or rather odd name, is related to well, the reason we gave it this name and the reason we constructed it as we did. A few years ago, I think, I don't know when exactly it was, Rob Speckens proposed the toy theory of quantum mechanics. The sort of motivation for this was to argue for an epistemic interpretation of the quantum state. And the theory was quite well received because it does seem to replicate many features of quantum mechanics. Now, the systems in his theory, they're all of one type, and they're intended to sort of be analogous to a qubit. Each one of these systems can exist in one of 4 different states, but these are the ontic states, if you like. These are the states which the system actually is in. However, the key feature of the toy theory is that the best knowledge that any observer can have about one of these systems is that the state is in, that the system is in one of 2 different states. And this restriction on the observer's knowledge is really what gives rise to all the quantum features of the theory. So, if you see, these are, these basically are the, if these are the 4 different ontic states, then the epistemic states, the states of knowledge that you can have, are essentially of these 6 types. And these are really exactly the the 6 states that we showed earlier form part of our category spec. Now, essentially, our claim is that all of the toy theory, all of the states and processes within the toy theory are also contained within our category spec. For example, evolution of a single system within the toy theory can occur in one of 2 ways. Either outside of times of measurement via permutation, which clearly by construction are present in the category spec, and also during measurement we get a sort of probabilistic evolution, which corresponds in our theory to morphisms of, for example, what do we have here? For example, all of the measurement sort of evolutions are morphisms of this form. The epistemic states of 2 systems are essentially derived by applying permutations to these 2 states. states of this sort are considered to be unentangled, to sort of be the analogue of separable states. And in our category, these can be seen either as sort of Cartesian product of these states like Z0, or by this combination here. We can also get these states out, which are considered to be the sort of the analogues of entangled states, via this combination here. I'm running a bit low. What I should probably just say is that essentially within the category spec we have all of the states and processes that are present in the toy theory, and so in a sense the success of this toy theory in replicating features of quantum mechanics can be sort of partly attributed to the fact that it's essentially an instance of one of these quantum-like categories. Okay, I should probably leave it there.
Questions, comments?
So if you looked at other things that have more than the four, so you're, as I take it, the actual state has like four things. You can't see all of them.
Yeah,
right?
yeah.
So have you looked at ones that have more than four, or is that not going to be as nice?
Well, I guess in as much as right, going back to category, the states are all the objects are all either of 4 or of sort of higher numbers of that. Have we? I mean, we've looked at them insofar as they replicate what appears in the toy theory. We haven't really done much on from sort of a priori from this category whether you get observable structures which are mutually unbiased of the right numbers. No, we haven't really looked at that.
I think the question is more to vary this category instead of putting 4 there, putting 5 or 6. And obviously this formulation, this concise formulation easily allows tweaking the category into sort of other models. But if this form exactly gives this nice qubit structure of X, Y, Z,
Right.
then you would get something else which probably has similar properties, but doesn't at all look like a qubit.
But there's also dimensions where you won't find enough unbiased things, right?
So
I'm not quite sure how general it really can.
Yeah.
But let's say if you can find those unbiased and prove them using the theorem, mathematics, be rich and famous.
I'm sure that ain't.
Maybe that's a nice point to finish for now. Okay, we'll reconvene.